Bismillahirrahmanirrahim. Assalamu alaikum. In this lecture, I will discuss commutation in DC generators. The currents induced in armature conductors of a DC generator are alternating. Commutator makes the current unidirectional. The direction of current in armature conductors under north pole is opposite to that under south pole. When conductors cross the magnetic neutral axis, the direction of current reverses. This process is called commutation. Duration in which coil remains short-circuited with carbon brushes is called commutation period. If current reverses completely during commutation period, commutation is ideal. If current reversal is not complete during TC, sparking is produced at carbon brushes and commutator contacts, which reduces lifetime of both. This is due to poor commutation. So the phenomena of commutation can be better understood by assuming this case study. And in this case study, you can see that we have three coils. And from the developed diagram of the armature winding, we understood that each coil terminates at the commutator segment. So this is one coil which is terminated over here, and that termination is connected with the commutator segment. This is another coil and it is terminated at this commutator segment. This armature coil is terminated at this commutator segment and so on. So these are three commutator segments A, B, and C, and this is the carbon brush. At this point, this carbon brush is in complete contact with this commutator segment B, and the direction of current over here is 20 amperes from left to right. It is 20 amperes from left to right. It is 20 ampere from right to left. So this can be understood as minus 20 amperes. Now this coil and these commutator segments are rotating and this carbon brush is stationary. So after some point, this commutator segment will be in touch with this carbon brush. So let's see what happens. We will analyze this scenario slowly or step by step. So here you can see this commutator segment B is also in contact with this carbon brush, and this commutator segment A is also in partial contact with this carbon brush. And now this coil B is actually crossing the magnetic neutral axis. So that's why its current is undergoing decrement or reduction. And when this coil crosses the magnetic neutral axis, which is specified by this carbon brush, the current of this coil will become zero, and when it crosses the magnetic neutral axis, its current will become negative, right? So now this is 20 amperes. This current has become 10 amperes because that has to reduce first, and then that current has to be negative. So this is 20 amperes and this is 10 amperes. So 10 ampere current will come in this direction and it will enter this commutator segment, and from this commutator segment it will enter this carbon brush. Similarly, 10 amperes of the current will come over here and 20 ampere of current is also coming from coil C, and collectively it will become 30 amperes and that will also enter this carbon brush. So 40 ampere current is again collected at the carbon brush as was observed in this case. Now half of this commutator segment is in contact with this carbon brush and half of this commutator segment is in contact with this carbon brush, and the current of this coil has become absolutely equal to zero, and this current is 20 amperes and this current is entering this commutator segment A. Similarly, this current is entering this commutator segment B, and collectively 40 amperes of current will be available at this carbon brush, and the current of this coil has become zero. Now this coil B is exactly at the magnetic neutral axis because we can see that this coil B is exactly facing this carbon brush. Now this coil B has to cross this carbon brush and we will get this scenario, and at this scenario its current has become minus 10 amperes. This is 20 amperes because this coil is not actually present in front of the magnetic neutral axis, so that current is 20 amperes, and this 20 amperes and this 10 ampere, it will become 30 ampere. So 30 ampere current will enter this commutator segment A, and this 20 amperes, and out of this 20 amperes, 10 amperes will enter this coil B, and 10 ampere will enter this commutator segment B, and that 10 ampere and that 30 ampere will be added, and it will become 40 ampere, and 40 ampere current will be available at this carbon brush. Finally, this is our coil A, and it is providing 20 amperes of the current, and this is our coil B. Ideally, the current of that coil should have been 20 amperes from right to left, or alternatively, we should have observed minus 20 amperes of current in this coil. But due to poor commutation, the current of this coil has reversed only up to minus 15 amperes, and this 15 amperes and this 20 amperes will become 35 amperes, which will be entering this commutator segment A, and that 20 ampere current will be divided to 15 ampere and 5 amperes, and that 5 ampere of the current will enter this commutator segment B, and since this commutator segment B is not in contact with this carbon brush at all, so that current will pass through this air gap and it will cause sparking over here. So this is called poor commutation and sparking due to poor commutation, and that sparking is actually produced due to incomplete reversal of the current in this coil which is undergoing commutation. So in coil B, complete reversal has not been achieved. If the complete reversal of 20 amperes had achieved in this coil B, then that current must have been 0 amperes and there would be no sparking over here. So this is the result of poor commutation, and that can also be visualized graphically in this graph. So this is our coil A, this is our coil B. Initially, both coils are operating at 20 amperes. This region corresponds to the carbon brush. When this coil B is crossing this carbon brush, ideally it should have followed this path, and up to this point, that current must have been reversed to minus 20 amperes, but due to poor commutation, this current has reduced rather slowly, and up to this point, that current has been reversed up to minus 15 amperes, and due to this incomplete reversal of the current in coil B, which is undergoing commutation, sparking is produced over here. The reason behind this delay of complete reversal of current is self-induced EMF in the coil. This EMF is called reactance voltage. So in order to minimize this sparking due to commutation, we have to use interpoles, and these interpoles are designed between the main poles at the yoke, and they have few turns and they are connected in series with armature winding, as was the case with the compensating windings to reduce armature reaction, which we discussed in our previous lecture. The polarity is the same as the main pole ahead in the direction of the rotation. So as their polarity is the same as that of the main pole ahead, they induce an EMF in the coil under commutation, which helps the reversal of the current. This is called commutating EMF or reversing EMF. It neutralizes the reactance EMF, thereby making the commutation sparkless. So here you can see these are the main poles. So this is the north pole and this is the south pole, and these are the main poles. These are the interpoles, and these interpoles are designed in between the two main poles. So this is one main pole, this is other main pole. So in between them, we will have the interpole, and the polarity of this interpole will be same as the next pole ahead. So if this armature is rotating in the clockwise direction, the next pole ahead is south pole, so that should be south pole. Similarly, the next pole ahead over here will be north pole, so that interpole should be north pole. And you can see here, this is a four pole stator, right? This is north pole, south pole, north pole, and south pole. So this is a four pole stator, and there will be four interpoles. Considering clockwise rotation of the armature, this will be south pole, this will be north interpole, will be south pole, and this will be the north pole. So these are the interpoles and these are the main poles. Both compensating windings and interpole windings are connected in series with armature winding, so they cancel the armature reaction and sparking due to poor commutation. So that is all about our today's lecture, and you must remember that compensating winding is used to minimize the armature reaction and interpoles are used to improve the commutation. And both these windings, interpole windings and compensating windings, are connected in series with the armature winding. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.